Hey, what's up, guys? This is Chung here, and so tonight, let's talk about this uh, another graph problem. It's called minimum height trees, number 310. So you're given a number of nodes here, n, and the different edges, and you need to find out all the root that can form the minimum height trees. So what does the minimum height trees mean, right? Okay, so it means that uh, so given like a node, right? Given like a node anywhere, so it can go into the on each direction, right? So for example, this one number node one here, right? Node one, it can go to three directions, right? So basically, it will have this one will have three paths to the end of of the graph, and the minimum of so basically there's three, three, and three, right? So and the minimum height, right? So you need among all the nodes, you need to find the nodes who has the minimum heights, which will be formed by using this current node as a root. So the height of a rooted tree is the number of edges on the longest downward path between the root and the leaf. So which means the longest among all the paths to the leaves, right? In this case, the all the path is one, right? So that's so in this case, there's the one root one will have the height one. How about two, right? Let's say how about zero, right? How about zero? What is the zero the minimum height of this one? It's gonna be two, right? Because you got one and two here, and for two is the same, right? If the two is the root here, and then it will have also two, right? Three, same thing. If you use two as a root, the height of the tree will be two. Same thing for three, the height of the tree will be two. So zero, two, right? One, one. This is the height, right? And this is the root, right? Two, two, right? And three is two. So among all this height, which one is the smallest? One, right? Then we'll be using one. So one is our one is gonna be our result. So same thing for this one. And root and height, right? Zero. What's the height of the tree being at zero? And one, two, one, two, one, two, three, right? So it's three, one, three, right? Two, three, uh, three, three is two, right? Because on this side, the height reaching to those nodes will be one, but reaching the other one is going to two. So the height will be the longest one, so it's going to be two, right? How about four? Four is also two, right? Because with four as a root, when it's reaching this side as to the leaf is one, but to the other side is two, right? So we get the longest one. How about five? Three, right? So what's going to be the result for this node, for this tree? This one, right? So that's why we have a three and four as a result. And with that in mind, I think the key point of this problem is that we have to get we have to get a conclusion that regardless of how big the tree is and how many nodes are in this graph, we can have like many nodes here, like zero. Uh-huh, right, this one. doesn't matter, right? It doesn't matter how many nodes we have in this like uh tree structure nodes, tree structure graph, right? The answer of this like minimum height tree can be at most 2. Why? Because I think it's kind of we can prove that. I think for example this one, right? It doesn't really matter because the the height of the tree will be like the highest. It will be the longest path to any node, right? So it has to be somewhere in the middle, right? Because if you go too too far to one side and then out from the other side, this tree the height of the tree will be increased. Let's say for example this one, right? If you go to the other side and then if you go to if you go to too close to the other side, then the height of the tree will become bigger. It's only when you like at at the very center, then you can it's possible for you to have all the have the minimum height, and the maximum you can have is 2, because otherwise, if it's not this 2 and if you move to the other, if you try to use this one, the height will be smaller. Sorry, the height will be bigger than those 2 nodes. Okay, so oh, okay, with that in mind, so I think we're gonna use the similar like the BFS topological sorting, right? Topological traverse basically, and so our logic is gonna be so we just keep uh removing the leaves node, right? Removing the leaves node until we only have 2 or less nodes in the current graph. For example, this one, right? So we just remove nodes. Uh, we remove all the leaves nodes. So in this case, the leaves node is going to be 0, 2, and 3, right? So once we remove all the leaves nodes, we only have one node here left, and one is smaller than 2, right? Then we'll have our result. So then 1 is our result. Same thing for this one. The leaf node is what? 0, 1, 2, and 5, right? So we remove 0, remove 1, remove 2, remove 5. And then we only have 2 nodes, right? So that's basically as we stop when there's only 2 nodes or less left in this graph, and the nodes left in this graph will be our result. Cool. So let's start coding, right? Mm, I think first I think we can check here, right? If n equals to 1, so what's going to be that? So if n is 1, then the which means the node is 0, right? So it's 0 base, as you can see here. 0 base 0 to n minus 1, right? So when n equals to 1, it means we only have one node, which is 0, right? And 0 will be our result, right? Which is return a, a array with only 0 in that array. And then like always, we also need to we have to construct the graph here. It's going to be the default list, um, default, sorry, not default list, default dictionary. Uh, its type is list, right? So u and v, right? From in edges, right? And we do what? We do graph u append v, right? And then same thing, since they're like undirected, we're gonna do like the other one, append u, right? So now let's get all the leaves nodes here. So what's the leaves node, right? So the leaves node, if you look at it closely, all the leaves node, there's only one edge connecting to that node, right? That's our criterion to determine if the current node is a leaf node. So um, let's see, we have a graph here, right? The graph, and let's do a node, right? Node for node in, right? In graph dot keys, right? So for all the keys we have in the graph, if the length, right? If the length of the neighbors, right? If the edges for this current node is one, right? Uh, if the length of this one equals to one, then that's the leaves, right? So we just do we keep doing this until the number until the nodes left is like uh is equal or smaller than 2, right? So we do a while n greater than 2, right? Then we just keep doing it until it's n is smaller, not greater than 2. So and then at the beginning we can just simply like update the n here, right? Since we already know every time we just get the leaves length, right? That's how many leaves we're gonna be removing at this one uh, BFS traverse, right? Leaves, right? And then what? So for each leaves, right? For each leaf in leaves, right? We'll be getting that the neighbor of that leaf, right? Which will be only one node, right? Neighbor. I'll just use neighbor here, right? So it's gonna be a graph, right? Graph dot leaf, right? So because we know the leaves will only have one neighbors, right? So this one, um, no, we can either do a 0, right, to get this one, or we can do a pop, or we can do a pop. It doesn't really matter if we pop this array or not. Why? Because let's say 0, I'll just use this one, right? 2, 3, and 4. So when we remove 1, since this node is like it's undirected basically, so that we'll be adding 2 edges here, right? So when we have 1 here, we have when we traverse remove 0 here, okay, so the neighbor here will be 1, right? So here then will be 1, and this leaf is 0. So for the 0, there's like an edge here, right? That's the edge from 0 to 1 and 1 to 0. That's how we do a graph here. It doesn't really matter if we remove this node or not, right? We can remove it or we don't. It doesn't really matter because once we add the neighbors here, we will definitely remove this node. Sorry, we'll definitely remove this edge, right? So that's after removing this one, the edge from 1 will become 0, right? So with this one, it's already gone, right? It's gone forever. So the edge for this for this leaves node, uh, we can either save it in a graph because we will never be visiting this node anymore because the path to this node has already been removed here. When I say removed, I mean this. I mean this one. Okay, so I'll just use a 0 here. I'm not removing this one because this neighbor here, I'm gonna do a graph dot neighbor, right? GHBOR. I'm gonna remove, right? So, but this at this time we cannot simply pop because we only want to remove the edge for this node, right? From 1 to 0 because we don't want to do a pop. If we do a pop, we don't know the sequence. It could be removing this one or this one, but we only want to remove that one. So the neighbor's edge from the leaf, right? That's we do a, and then if we do a after removing, we'll check the length, right? To determine if this after removing that edge, if this current neighbor will be a valid leaf, right? Same thing if the length of this one equals to 0, right? We just do a oh yeah, let's do a we need to define new leaves set here, right? And then new leaves dot add, right? We add this neighbor basically if it has already become a leaf. As you can see here, since we'll remove this the edge from 1 to 0 anyway. So for this edge, it doesn't really matter. We can either keep it here or we can just use pop dot pop, right? Either way is fine. And okay, so uh, okay, so where am I? Where was I here? We do that, and then yeah. So in the end, we will be assigning this. We'll be updating. We'll be assigning this leaves with this new leaves array, right? Basically, for the current leaf, we just keep removing the edge for the neighbors, and if neighbor had become the leaf after removing the edge, we'll add this neighbor as the new leaves. And in the end, after the for loop, we update the leaves here, right? And then what? In the end, we just return the leaves, right? So whatever left in the leaves here, right, will be our result, because in the end we'll be assigning the remaining leaves to here. In our case, it's gonna be our result if n is like smaller than or equal than 2. Let's try to run it. All right, cool. And yeah, I don't know what else I can say. So basically, just a key concept here is that we have to know that there can be only 2 node at most to be our final result, right? So and then we just keep removing we're just doing the like topological sorting, right? Topological sorting by removing doing the BFS, right? So each time we remove all the nodes, right? All the leaves nodes from the graph until we only have 2 or less nodes left, and then that will be our result. Okay, cool guys. I hope you guys enjoyed the video. Thank you so much for watching it. And time for bed for me. Yeah, I'm going to sleep now. All right, I'll see you guys. I'm thinking maybe tomorrow. All right. Good night, guys. Bye.